This video is going to show you how to do problem 29 out of chapter 10. So here's the way this problem reads. Some recent poll of 1,235 randomly selected likely voters. So let's just stop there for a second. That's specifying our sample size little n. Shows that your candidate is ahead with 52.1% in favor. Okay, so this is a percent that's coming from our sample, therefore it's a P. There are only two candidates. Use hypothesis testing to infer to the larger group of all likely voters. So carefully identify a two-sided hypothesis. To avoid the scratch pad right now, what I've done is to type this up. So let's say that pi is the true percent in favor of our candidate. So if we could go off and interview all likely voters, we would know pi. Now what we care about in this problem is whether we're ahead or behind. The cutoff for being ahead and behind is 0.5. Therefore, our null hypothesis is going to be that pi is 0.5, and then let's use a two-sided alternative. So before we look at the data, we don't really know if we're ahead or behind. Therefore, we'll be conservative and use this two-sided alternative. Now, the given has specified that we have a sample of 1235 and that our P is 0.521. To use hypothesis testing, we always start by assuming that the null hypothesis is true. So we're going to assume that H naught is true, implying that pi is 0.5. Now let's just go draw the sampling distribution. So I have to go find that sketchbook. And so this is what our sampling distribution is going to look like. So it's going to be approximately normal since we have pretty large sample size. This again is the sampling distribution of P. Now under the null hypothesis, the mean of this distribution is 0.5. Now we've gone off and sampled 1,200 and some people and observed a P of 0.521. What this problem is going to cook down to is we need to find the area in this tail, and then once we know the area in that tail, we'll go double it to get our p-value. So the combined area of these tails gives us our p-value. So let's go do that. The first thing that we need to do is to determine the standard error. So, well, actually we have a choice in this situation. We can either find the standard error or the standard deviation of p. So this is only possible in the case of hypothesis testing for proportions. So notice we've just assumed that pi is 0.5, therefore we can use the formula for sigma sub p. So the formula for sigma sub p is pi times 1 minus pi over n, which is 0.01423. So I always like to write my standard deviations next to it so I don't lose track of it, 0.0413. Now, ordinarily, with hypothesis testing, we don't know sigma sub p, or we don't know the true standard deviation of the sampling distribution, and we have to estimate it with S sub p. So how would we find S sub p? Well, S sub p is 0.521 using our p times 1 minus p over n. And what you'll see is it's equal to sigma sub p in this case to, it looks like 3 decimal places, 0.0142, and then standard deviation has a next digit of 3. Here we have a next digit of 1. So it's really close. So, if you want, you could write, but this is just approximately the same thing as S sub p, which is 0.043. That should be a 2 there, shouldn't it? 1. All right, so let's go find the area in that right tail. So what was that right tail? Well, it's just the chance that we observe one of these p's from our sample that's bigger than 52.1%. So what's the chance of observing p greater than that? Well, this is going to be approximately equal to the chance that I have a z value greater than 0.521 minus the mean. Now I'm going to drop in the standard deviation since I know it. If you were to drop in the standard error, I would give you full credit. So that's also acceptable. And we end up with a z value of 1.48. Now I would use norm dist, so take 1 minus norm s dist of 1.48, and so you get the tail probability is about 7%. I'm going to go write 7% in here. Therefore, the area in this other tail is also about 7%. That's a 7 right there. And therefore, our p-value is about 14%. Since that's greater than 5%, we can't reject the null hypothesis. So our conclusion then is the race is too close to call with this sample. Okay, so there's a substantial enough probability that we've come to a we have an unlucky sample. So in other words, if the race were tied, or worse yet, if we were just a tiny bit behind, if we had 49.99% of the vote, then note there's a substantial probability that we would have drawn such a sample, giving us a p indicating we have 52.1% of the vote or more. So we would just say that this race is too close to call with this present sample. Well, we could also do this problem using the confidence interval approach. So here's how we do that. Remember, the confidence interval approach says go find the 95% confidence interval. There's one small point that I want to make. With the confidence interval approach, you don't know pi. Therefore, you must use the standard error. So here's the standard error. We go 2 standard errors out from the mean, and we get a confidence interval extending from 49% to about 55%. Then we would note that since 1/2, our reference value of 1/2 is in that confidence interval, we cannot reject H0. So, again, you get full credit on an exam for using either the p-value approach, so finding 14% and saying it's greater than 5%, or by using the confidence interval approach. Let's go back to the course packet. Now, part D says repeat parts B and C, assuming that the percentage is 58% rather than 52%. So let's go do that. Notice that the math is the same. What's the chance that I observe a p greater than 0.583? Well, it's approximately equal to the chance that I have a z greater than 0.583 minus the mean. Now notice the standard deviation of the distribution doesn't change. I'm still using 0.01423 because we've assumed the null hypothesis is true, and that standard deviation of p is based on 0.5. It's not based on the sample value. In this case, your z is huge, indicating that you have a p-value that's approximately 0, therefore we reject H0. Likewise, the confidence interval extends from about 55-56% all the way up to 61%. That doesn't include the value 0.5, and so we reject H0. So either approach says we can call a race if our lead is, if we get a sample saying we have an 8-point lead, can't call it if the sample just says we have a 2% lead. Let's go back to the problem. Explain why a one-sided test would be inappropriate here by showing that each of the 3 possible outcomes of a two-sided test would be of interest. Well, if the 3 outcomes are either you're ahead, you're behind, or you're tied. So clearly, if you're ahead, well, if you're behind, you probably want to change what you're doing. If you're ahead, you want to keep doing what you're currently doing. And if the race is tied, well, you probably want to change what you're doing as well. You want to differentiate yourself from your opponent. All right, that's how you do a test for a single proportion.